Hello and welcome to our Python tutorial series on deep learning by Deep Learning School. Today we're going to cover a model of Neuron. This is a plan of our lecture, recap of linear models. We'll talk about gradient descent and its variations, and actually we'll train Neuron, raw neuron, and with activation functions. Let's talk about one-dimensional regression. The problem is to predict y given some x, where y is some target value we need to predict. For example, house price given its area. Area in this case is feature, and it will go with letter x. And in linear regression, we assume that our target distribution is linear. And for example, we can predict annual sales of some shops given their areas. Let's watch at this table. This is data set of houses. We can see some features, bathrooms, views, great. And we need to predict the price of the house. They're in red boxes. So how would we solve this problem with linear regression? We have sigma sign sum of weighted features. We just multiply each feature, for example, floors, by some number. Our model will learn how this feature is important for us. And W sub 0 is our bias. In fact, we can represent this formula in matrix form. Take a look at this. Y is vector of targets, W is vector of features, and X is a vector of features, and W is a matrix of weights. And epsilon is some random value that represents randomness of our data set. So in this case, we'll have 100% fit, but we don't know this random epsilon. So how would we represent this task in matrix form? We'll add fictitious variable, a column of ones to the x values. So in matrix multiplication, we'll get this beautiful formulas that are indeed similar to our formulas for linear regression. And so, yes, the task is to predict weights, W. Okay, let's recap gradient descent. I guess you are familiar with classic machine learning algorithm ordinary least squares, OLS. Let's watch at one-dimensional case. So remember, our target is to predict weight, omega. And we'll represent this target as minimizing the squared error. In multidimensional case, our goal is to predict multiple W's. This task is harder, but we again solve this by minimizing our squared error. But what if we need more general case? We don't want to just divide our data set with a line. What if our pattern is more complex? That's where we need something more powerful. So, general case. Our goal is minimize some loss function, not just squared error. And here comes gradient descent. Our goal again is to find parameters vector with some loss function. And again, we solve this by minimizing a loss function, but in gradient descent, we do it differently. But what gradient really means? Let me introduce you to gradient, mathematical operator. This function, given your formula, will give you some vector field, actually. This information about function growth. So given this information, we can climb hills. Yes, but actually we need to go downside and find some interesting minimas. Consider the following example. Let's estimate we are given some parabola, and it's our error function, loss function, and our goal is to get to the minima. So how would we do this? Let's look at the formula down below. It says basically go the opposite way gradient points us. So gradient points us this way, and we'll go just in other direction. It's worth mentioning that we have this term alpha. It's just some number like 1,000th, and it will shorten our error in some way. So we'll don't jump like this around. And let's see, we'll just go down like this, and when we'll jump over the global minima, we'll go another way, because derivative changes sign. And eventually we'll come to the bottom of this parabola. Remember, we're traveling here in parameter space, so this value actually is omega. You can build an intuition about it. It's like running down the mountain with a flashlight when it's dark around. This is essentially in the nature of derivative. You can look at the function in some close-up neighborhood, and not you can see all its properties behind this neighborhood. Okay, let's sum up. Gradient descent is computed all over the data set. You compute your loss function for every instance in your data set, and just sum them up with some coefficient alpha. And we'll just repeat this step by step until this thing converges. That's not the general case. It rarely will converge, actually. And the reason people invented stochastic gradient descent, it's less likely to stuck in local minima. Let's recap what local minima is. Let's draw such parabola and another one, and we get this point. You can look at this like in close-up, that it's actually a mountain, and algorithm given this point will consider going left. That's not the way we want. Our global minima is in here. So what basically gradient descent does, it will jump here, 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 and stuck here. But stochastic gradient descent is different. You'll compute your losses on only one instance in dataset. So imagine like you have 2 million pictures of cats and dogs, and you'll train giant neural network on only one picture. What would it be? It will be rather bad, but there is some advantage of this algorithm. So the difference you can see here, it's only in this sign for gradient descent, and stochastic gradient descent is computed only on one instance, but for several times. It's worth mentioning that gradient descent basic, when we compute our gradient on all the dataset, will converge gracefully on some smooth function, and actually without little bumps like I drawn with two parabolas. Let's watch how both of these converge, and you'll get why stochastic gradient descent is quite better than gradient descent. Here you can see how gradient descent very confidently converges to local minima. But imagine it will have some pit on its way, and it will just stuck in it. Let's move on to stochastic gradient descent. You can see this random moves stochastic gradient descent does. It basically in sometimes goes away from our global minima. So you would ask, what's the point? But you can see it when it stucks in some pit. It will just jump over it, because it's kind of stupid, but it will get to the global minima better than basic gradient descent. So let's compare these two algorithms. SGD updates weights faster, but takes more steps to converge. We saw it on GIF. SGD works well with functions with lots of local minima. We're also seeing this. It will just eventually jump off the pit. But gradient descent works good for just convex functions. It will converge more confident. But what's the trade-off between these? We can actually use a mini-batch approach, which is common known in all the state-of-the-art deep neural networks. Basically, we'll just compute our gradients on batches of, for example, 16 pictures of cats and dogs, or 32. These are common values. Here you can see convergence of SGD descendants. Momentum, RMS probe, Adagrad. No one can predict which one will work better in their task. So I suggest you just to try all of them in your problem. Let's move on to what Neuron is. We are familiar with linear regression task. Actually, we can modify this thing to get a mathematical model of human neuron. Take a look on our modified linear regression model. We can just squash its values with sine function. Sine function just answers you a question if your value has a positive sign or negative sign. In negative case, you'll get 0. In positive, you'll get 1. Let me clear it out for you what activation threshold is. That's a common question. Why we need another some free term in our activation function. So basically, consider this example. You have 0 as x and 1 as target. Oh, that's a bad error. Okay, it's x and this one is y. So you will never be able to get 1 from this function if you have no bias in here. Let's see our biological inspiration. So this is human neuron. It has several of dendrites. We assume they're just weight potentials on the dendrites and go to sum up in core of neuron, and then it will put some potential to the axon, and axon is exit output of our neuron. And this is our artificial neuron. It has inputs. It's like dendrites. Here we weight, for example, x1 by omega 1. We just multiply them. It go to sum. It's to summing function. It squashes with activation function, and the single output of our neuron is here. And the beauty of this little mathematical mechanism is that we can stack layers of it, and it will earn more power than you would expect. Let's see how we'll learn train one neuron. So we're given its loss function. No, it's activation function, and we'll need actually to derivate it by omega sub I. Let's learn how to train this thing. So how our loss function will look like. It's x over w in some activation function minus target and squared. This is our mean squared error. And we need to take partial derivative by some parameter omega y. This is just one number in our model. For example, in several millions of numbers of parameters, we need to adjust to make our model to predict better. So let's take it. I need delta sign here, and it will go like that. Sigma of x times omega minus y, and derivative of inner function. Y is constant, and derivative of sigma. Let's put x and its derivative. Oh, okay, I write it. And derivative of inner function. Okay, what's x times omega? Where is the only parameter, omega y? It's hidden in omega vector. Let's actually clarify this. Okay, x. Let's take x as a row. Dummy 1 for bias. Oops. x1 xnth times omega 0, our bias, omega 1 again, and it's gonna be bias plus weighted sum of parameters. Let's make it j equals 1 to n. Okay, when we differentiate omega 0 by omega sub I, it will be 0, and so on for all terms except one, where omega sub I is represented. So xi omega I, we need to differentiate. Actually, yeah. This is true. So it's just x sub I. That's the last term we need to add in here. It's multiplication. And here we go. This is our part of our gradient that we need compute to train our neuron. And it's actually one partial derivative. To make it gradient, we need to make column of this. So let's make it like df by d omega 1 and so on. You need to subtract the thing with learning rate from our parameters. Okay, we learned how to train these things. We were not suggesting some activation function. We just take some sigma. And what a coincidence, sigmoid is represented by sigma. It's a smooth function, goes from 0 to 1 smoothly, and actually we need to use it instead of simple threshold function because it simply has a smoother derivative, and we can actually get smoother values, not just 0 and 1, but something between them. And the thing is that we can interpret these values as somehow as confidence of our neuron. For example, if you're guessing what's on a picture, whether it's a cat or a dog, you'll better get 0.8 rather than 0.5, which is just a random guess. Oh, this way. And actually you have choice of plenty activation functions, like rectified linear unit can be seen here. Just a simple function. It can be represented as max of 0 and x. And its beauty is its simplicity. We can compute it like tau, not as a sigmoid which has some exponent in it. And it's the most popular in deep neural networks, because when you have millions of neurons, you'd better save time. And there are several modifications of it, like Ricci-Relu, which helps you with smoother gradients, and plenty of them, just plenty. You're not restricted at all. The choice of activation function is based on the task you're solving. And actually we come to the end. Let me introduce you to several links I think are important. This is a link to the Siraj Raval's video on activation functions. Great channel, great videos. Check out article by Stanford and article on activation functions by Jamie Jordan. And that's it for today. Thanks for watching.